So thanks a lot for your introduction and welcome to everybody. So today I would like to report about the current state of my alternative pressure solver SCARC. So in fact, its development has been going on for many years right now, and I have already reported on it a couple of times. But as all of you who also work scientifically will most probably confirm, the development of numerical code is something like a never-ending story. So as soon as you have done one big step, the next 5 are waiting for you. And the deeper you go into the stuff, the more you recognize all the difficult interconnections in between and all the possible troubles. In this sense, I can only give you a snapshot of my current work in progress. But I really think that some very fundamental steps have been taken right now, and that SCARC can be applied to a variety of different cases, even if there are still limitations, and even if there is still a lot of room for optimization. I will come back to those points at the end of my talk again. So, well, the all-embracing topic behind is the efficient solution of the FDS pressure equation. And in fact, there is already a very powerful pressure solver, namely the FFT solver, which I will shortly summarize. And besides, there is also an alternative pressure solver named UGL-MUD, which was developed by Marcos Varnella, which I also will talk about. So you may ask, why is there a need to still have another pressure solver? And this is just the story I would like to talk about today. I would like to point out that there is not the one and only pressure solver. It depends on the situation, and I would like to discuss all those points with you. Okay, then let's first have a look to the pressure equation in FDS. So don't be afraid, I don't want to lead you in a mathematical jungle today. It's simply to know the basic properties of this equation. So from a mathematical point of view, it's an elliptic partial differential equation of second order, which is also well known under the name Poisson equation. And the most important things to know are here, what you can see here. It is strongly coupled with the velocity field, which will be important. Besides, we have a huge source term where all the different contributions from the last time steps come in. So it has to be solved at least twice per FDS time step. And you know there are a lot of time steps. So it's very important to do it efficiently and to do it accurately. But I think the most important property of this equation is that it has something like an infinite speed for the propagation of new information. So if you get a new information, even if it is very local, then this information immediately spreads all over the whole domain. And if you think of a parallel solution of this problem, where you break up your domain into subdomains, then it's very important that your parallel solver is able to reproduce this very fast speed of velocity of information propagation. And you know, if we want to compute this equation on a computing system, we have to make it finite, we have to bring it on a grid, and to this end, a finite difference method is used in FDS, which makes use of these matrix stencils, which simply describe the physical relations between the single grid points based on the elliptic equation. Now, before I explain the concepts behind the different solvers, let me introduced a very simple demo geometry. It's an angled pipe domain in 2D. We have an inflow on the left-hand side. We have an obstruction in between. And we have an open outflow on the right-hand side. Now, the first obvious way of proceeding would be to discretize the whole domain. We use a huge grid for the whole domain, and we end up with one global matrix. But we want to do it in parallel, so we can also use a set of local discretizations. And then we end up with a set of local smaller matrices. And now the crucial question is it really the same if we do it on one global grid or if we couple a collection of local solutions? Do we really have the same quality of approximation? There is still another issue which is very important. So if you look to the left mesh here, only to the left mesh with the internal obstruction, then there are also two different possibilities how we can discretize this mesh. And this is related to all cells which are internal to this obstruction and which are surrounding it. So this is mesh 1. First idea could be to use all grid cells, no matter if they belong to the obstruction or not. In this case, we have the advantage that we can use the same metric stencil everywhere, no matter where it is in the domain. So now you might ask, isn't that a little bit unphysical? Because we have a solid obstruction here where nothing happens. So we could exclude those cells from our system of equations. But in this case, we have to use more intelligent matrix stencils. So this one here disappears, and this one doesn't have a leg reaching in the obstruction anymore. So it's much more complicated what we have to do. Now, when we have a look to the resulting structure of the system matrices, in the structured case, our Poisson matrix has a very regular shape. It's a sparse matrix. It has only very non-zero elements. Usually it has only 7 diagonals. But this is only a 2D case, so we only have 5 diagonals. But here, you see, it has a very irregular structure. It's the same everywhere. And this has a huge advantage, namely, we are able to apply highly optimized solvers, as it is done in FDS with the FFT solver. Those solvers exploit this regular structure of the matrix. If we use the unstructured discretization instead, then this regular shape gets lost. There are regions where we don't have this structure. So for this simple example, it looks quite fine. But imagine you have a complex geometry with a lot of internal obstructions, with a lot of walls or complex geometric details. Then the matrix might be very irregular. And then we cannot longer apply those highly optimized solvers. We have to use more robust solvers, but they are slower, unfortunately. So please keep in mind most important points from this section. There are 2 ways to discretize with respect to the meshes. We have a global or a local discretization, and we have 2 possibilities to discretize with respect to obstructions, namely structured and unstructured. Now let's have a look to the current FFT solver. The FFT solver is based on local structured discretizations. So in each mesh, a local Poisson problem is solved by a highly optimized local FFT method, which is taken from the optimized package Crayfish Pack. And this one has proven to be extremely fast and robust over the last years. In fact, I don't know any Poisson solver which is faster. But in order to solve those local problems, we have to specify boundary conditions there, all over the mesh domain, not only at the external parts of it. But these values are not known at all. They can only be specified approximately. And to this end, the meshes have to communicate to each other because they simply take their own average from the last time step to set the new boundary data. So we need a local communication there. Now let's have a look to the resulting flow field. Remember, we only have local discretizations. So how accurate can it be? Have a look to this special position here at the transition between mesh 2 and mesh 3. Because we only have local discretizations and we don't have the correct boundary conditions there, there might be an inconsistency between the single flow fields. And there is still another issue. If you look at the obstruction here, we only have a structured grid, and on this grid it's not possible to describe the boundary of this obstruction, so there might be a penetration of the flow field into this obstruction. So in most cases, these errors are very, very small. But it might happen that we end up with a situation where there are slight inconsistencies and a slight penetration. But fortunately, there is a way to correct it. And it is done in FDS by an additional corrective iteration, which is called pressure iteration. And those local FFT problems are not only solved once, but a couple of times until those errors are driven below a predefined velocity tolerance. And usually it converges very fast. Now let's have a look how it looks like. Suppose we have done those local FFTs once. We end up with some inconsistent situation and with a penetration here. We perform a couple of pressure iterations and then gets more and more consistent. And the penetration gets less and less. And finally, we end with a fine situation, which is accurate along the mesh interfaces and accurate along the internal boundaries. So, but again, what about the conversion speed? As I told, usually it's very fast. We only need a handful of pressure iterations, usually, mostly only 2. And I think the default value is 10, which is hardly reached. But there may be situations where it is slow. So imagine, please remember what I told you about the basic key property of the elliptic equation. Namely, it's very fast propagation velocity for information. Now, look to a new information on the left-hand side. What happens with this information if we only have local discretizations? So in the first step, this information has only the chance to reach mesh 1. Then a communication takes place between mesh 1 and mesh 2 in order to specify the new boundary condition. And then this new information can reach mesh 2. The same procedure takes place again. we have a talk between mesh 2 and mesh 3, and the information comes to mesh 3. And finally, it reaches mesh 4. And it's obvious there is some kind of a time delay compared to a single mesh solution of that stuff. So if you only have 4 meshes, it doesn't matter usually. But if you have 400 meshes, it might be different. So suppose you have a long tunnel with steadily changing inflow conditions, so it might be hard for the pressure iteration to converge. So convergence can be slow. Okay. So let's talk about the next solver, the UGL-MUT solver, which instead is based on a global, unstructured discretization of the whole domain. And I think the U stands for unstructured and GL-MUT for global metrics. This solver also makes use of a highly optimized library, namely of the Intel math kernel library, and it is based on a global LU decomposition of the Poisson matrix A, which is again based on the Gaussian elimination process. It decomposes the matrix A into a lower triangular matrix and an upper triangular matrix. In our case, both are the same because we have symmetric problem, so we only have to store L. And those matrices are distributed over your computing system. And because we talk about a global and an unstructured solver, it's fine along mesh interfaces and along internal obstructions. There are no errors. But there is nothing good without something bad. If you look at just this simple 3D cube, which is refined more and more. And if you look at the storage needs for this simple problem, then you see it might be huge. The green bars are the storage needs for the sparse matrix A, and the blue bars are the storage needs for the matrix L. And please note, this is a logarithmic scale. As you can see here, in the case of 128 to the 3 grid cells, L takes 240 times about more storage than A, more double precision values, which is a lot. But these are 2 million unknowns. So if you have a computer at hand, this need may exceed the storage capacity of your parallel computing system for realistic problems. Okay, now this was a long story up to now to explain the need of a potential different pressure solver, and finally we have reached it. Its name is SCARC, which stands for Scalable Recursive Clustering, because it's not only one solver, it's a class of solvers which can be generalized in many different ways. It can be scaled with respect to different parameters, and it can be applied recursively. It can be clustered with respect to the single component. So it doesn't matter at the moment. I only would like to describe the very basic core of SCARC today. Its basic design principle, namely, SCARC is also based on a global structured discretization in the first step. So we have a global iterative method which really works on the global Poisson matrix, not on a set of local ones. And all the iterative components of this method are performed in a data parallel way, which means that they produce the same results as the corresponding serial method. Additionally, I also have local iterative methods. But they are not used as standalone solvers. They only are used as correction for the global method, for the global basic iteration. And in this sense, they only are used to provide a high local accuracy. Additionally, I use local data transfer between the meshes, and especially global one. The global communication is more expensive from a computational point of view because the processors have to wait and to synchronize. But on the other hand, it provides much more of the global of the global data transfer. So, in its basic version, it's also using a structured discretization. So there can still be errors along internal obstructions, the same as for the FFT. But as I told you, there are a lot of ways to generalize it. So I can also use the same pressure iteration as for the FFT, which I do in the default version. So the pressure iteration can be used to reduce those internal obstruction errors. But I can also use an unstructured discretization from the scratch. So there are no errors at all. And related to the global and local basic iterations, there are a lot of different possibilities to generalize. So the default version of SCARC, which is available in FDS, is based on this combination. Instead of the global iterative method, it uses a global data parallel conjugate gradient method, which is a well-known method, which is very robust, which uses global scalar products and provides a rather good global data transfer. Additionally, in the default version, I use the pressure iteration to reduce the errors along the internal obstructions. But locally, I can also use high-performant FFT methods to provide the local accuracy, which I do. It's the same FFT method as in the basic solver. And in this case, I'm fine. No errors along interfaces and obstructions. But there's still another way to optimize the global method. If I use data parallel multigrid instead of the conjugate gradient method, then I still have a much stronger global coupling, because this class of methods uses not only the fine grid level, but a complete hierarchy of grid levels, which all work together, which are interconnected by interpolation up to a coarse level, which provides the basic global data transfer. And this class of methods gives by far the smallest convergence rates. So, and finally, I have a basic default unstructured version, which is called SCARC. It also relies on the global conjugate gradient method. But as we have an unstructured discretization now, we can no longer use the FFT methods for the local preconditioning. Instead, I use the local LU decomposition, which is also based on a highly optimized library, the same as for the UGL-MAT solver. And because I only use it locally, the storage need is not that high as if I used it for the whole domain. So that's the current state. There are a couple of different versions, and I'm still working on optimizing those single components just to exchange, for example, the geometric multigrid, which I use currently, by an algebraic multigrid, because I have more freedom to choose the grid sizes there. I intend to also play around, with local incomplete LU decompositions because they are not that expensive. I would like to introduce OpenMP into the code and optimize the different parameter settings. And currently I'm in the process of running a lot of different verification cases which are available. And next step will be to start with validation. So I hope I could give you an idea of the possible issues behind the pressure solver, and I hope I will be able to report in 2 years about the newest steps. So thank you for your attention, and I'm open for questions.
Thank you, Susanne. It's been a long road of solving. Good to see some progress. Questions from the room? Randy.
Hi, Susan. Thank you very much for a very nice talk. So I think what I will give you a chance or prompt you to advertise what I think the sort of the main benefit of SCARC over GLMAT, because for unstructured, you also have the same, GLMAT can also be distributed, and so you have the same memory issues locally, okay? But you, I think, will have the ability to do coarse-fine mesh interfaces with SCARC, correct? Okay. GLMAT at the present cannot do that. It would be, I think, a very labor-intensive effort for us being Marcos, to work on that. So our sort of main hope is that SCARC is going to be able to handle that.
I think so.
And so maybe you could speak a little bit about that, just a couple of minutes, because that to me is a huge advantage of SCARC over any of these other solvers.
Anyone else? Oh, there we go.
So just to understand, SCARC then has no OpenMP embedded yet into it, but it does have MPI capacity on supercomputing. And my wonder is, how does it scale on clusters, on CPU clusters?
The scalability is a big issue, and it really depends on the global method which I use. The CG method doesn't scale that well, because it only uses global scalar products. The multi-grid methods have a bigger potential for scaling towards hundreds of meshes, I think. But I still have to optimize the local smoothing procedure. So we still have to work on it, on the scalability. But there is a lot of potential. I also used situations where I only coupled it with one coarse grid. I had a fine grid and only one big coarse grid, not all the levels in between. And this looks quite good because it reduces the convergence rates, because it provides only a basic global information transfer.
All right. Thank you again, Susanne.
Okay.